Welcome back, everyone. So this is going to be the lecture for the second experiment for the OChem lab. It is the synthesis of Stilbene. So you can follow along with me on your textbooks, section 28, pages 366 to 370. So what is Stilbene? There's actually two conformations. We have the E Stilbene, or the trans Stilbene, as well as the Z, or the cis Stilbene. So both of these are stereoisomers of each other. And so because of that, we can see that they actually have the exact same molecular formula, C14H12, C14H12, as well as the same molecular weight. However, like many stereoisomers, their appearance and properties can actually differ. So we can see that our trans Stilbene is actually a solid at 23 degrees Celsius, while our cis Stilbene is a liquid. And if we go further, we can see that the trans Stilbene has an incredibly high melting point of around 122 to 125 degrees Celsius. Meanwhile, cis Stilbene is 5 to 6. So the cis Stilbene also has a boiling point of around 307 degrees Celsius. And finally, both Stilbenes are not miscible in water. So other names for Stilbene, you can also call it 1,2-diphenylethene or 1,2-diphenylethylene. So remember from our last experiment, what we did was we purified our benzaldehyde, so we are working with a pure benzaldehyde product. So now what we want to do is we want to react benzaldehyde with this benzyl triphenyl phosphonium chloride. We're going to react it with sodium hydroxide as well as dichloromethane, and our products will end up being a mixture of both the E and the Z conformations of Stilbene. So this will leave us with three byproducts: the triphenyl phosphonium oxide after we've removed this benzyl, sodium chloride, as well as water. So the first thing that we want to do is we actually want to start by making our reagent. We want to make this benzyl triphenyl phosphonium chloride. And so the way we're going to do this is we're going to react triphenylphosphine with benzyl chloride. So you can see that the electrons on the phosphorus atom can easily attack this carbon and kick off the chlorine. And this can be done with any halogenated benzene ring. So we have benzyl chloride, but you can also use benzyl bromide, and the reaction will still occur the same way. So phosphorus attacks this carbon, knocks off the chlorine, and what we're left with is this benzyl triphenyl phosphonium chloride salt, where the benzyl triphenyl phosphonium is the positive charge and it's counteracted by the negatively charged chlorine. So this is usually out where we would start the lab. We wouldn't actually have to make this. So now that we have the benzyl triphenyl phosphonium chloride, we can actually begin the reaction. So this is a very famous reaction designed by a scientist by the name of George Wittig. It is known as the Wittig reaction, and we're going to use a very special reagent known as the Wittig reagent. So when we add sodium hydroxide, the OH is actually able to come and deprotonate this carbon. By deprotonating the carbon, we can have a double bond form right here by the phosphorus to form this product, which is our Wittig reagent. What's very good about this Wittig reagent, because we can kind of write it in these two resonance forms. So we have our double bond phosphorus here, and another way we can kind of split the atoms or the charges is to have a positively charged phosphorus and a negatively charged carbon. So this negatively charged carbon can also be moved anywhere along the benzene ring. So just make sure that you follow the resonance forms. So like this negative charged, it can be moved here, and then the double bond can be moved back. And you can keep moving this negatively charged anywhere around the benzene ring, and same thing goes for this positively charged to any of the other benzene rings. But what's important is that now that this carbon has this negative charge, it can actually attack this carbon, the carbonyl carbon, and bond right here. So what we're left with is we have the carbon attack our benzaldehyde. So our benzaldehyde is attached, and this is not very stable. So the negatively charged oxygen will now attack the positively charged phosphorus to form this oxaphosphelane. So this is the second step of the synthesis of stilbene. So once we have oxaphosphelane, it's going to undergo a rearrangement because remember, four-membered rings are very unstable. So it's going to just break apart where the phosphorus will take the oxygen, and we will get a double bond formation in between the two benzene rings. And so because this step is going to be kind of random, we'll end up having a mixture of the E and the Z stilbene. And so this is the final step of the stilbene synthesis. What's very good about this synthesis is that it's a one-pot synthesis. So if I go back up, all we really do is we're going to be adding benzaldehyde, our Wittig reagent, sodium hydroxide, and dichloromethane into one separatory funnel, and the entire reaction should go through in this funnel. So this is the actual procedure of the synthesis of stilbene. So we would begin with a 125 ml separatory funnel, and we would first add 3.9 grams of the benzyl triphenyl phosphonium chloride. Once we add a chemical, the next thing we want to do is wash any of the remaining powder with our solvent, that 15 mLs of dichloromethane. So now we've added our benzyl triphenyl, our triphenyl phosphonium chloride. The next thing we would want to do is add our actual benzaldehyde. So this is what we're going to react with the triphenyl phosphonium so that we can form stilbene. So finally, we add the sodium hydroxide, because remember, this is the mechanism that starts the conversion of the benzyl triphenyl phosphonium chloride to our Wittig reagent. So without the sodium hydroxide, the reaction won't occur. So once we add it, we kind of shake the separatory funnel to allow for the chemicals to mix, occasionally releasing pressure either by taking off the cap or opening up the hole just to let out any excess air, any excess pressure. Once we vent it a little bit, we'll add an extra 20 mLs of dichloromethane and just continue shaking. And then finally, we just let the separatory funnel sit so that the layers can separate. So what we should expect is two distinct layers. The top should be our organic layer that contains our stilbene, and the bottom should just be the aqueous waste. So what we'll do is we'll drain the aqueous waste first, add a bit of tap water to the separatory funnel just to kind of clean it out, and then we'd collect the lower DCM layer into an Erlenmeyer flask. So remember that the dichloromethane layer is what's going to contain our stilbene. To make sure that we remove any water that might be in our product, we just dry our product using that magnesium sulfate. So we just mix it together, and then using gravity filtration, we remove the magnesium sulfate and just collect a pure stilbene product. So with that would be the entire procedure to synthesize stilbene. So in case you ever need, in case you don't know how to set up the filter paper whenever you use a funnel, here's a nice simple diagram. We want to make sure that we have this kind of star shape so that we can basically we can collect as much liquid as possible. So just a couple things that if you were to run this experiment to just pay attention for. So because we're shaking the separatory funnel with some volatile solvents like dichloromethane, it's going to cause pressure inside the funnel, which is why we release the cap or open up the hole at the bottom to just vent out the pressure. We don't want the pressure to get too high because it could cause the funnel to break, or the separatory funnel to break. Another thing is we're using a very high percentage of sodium hydroxide, which is extremely corrosive. So always follow proper lab safety and wear your safety goggles and gloves while working in the lab. If for some reason you spill sodium hydroxide onto your skin, just immediately wash it under some running tap water and you should be fine. In terms of our solvents, just remember it's very volatile and can be toxic. So try to always keep the whole separatory funnel and anything like the entire reaction inside the hood, just so that we can prevent any kind of danger. So just to go over the waste. So for solid waste, we're going to have that magnesium sulfate. For aqueous waste, it is that first layer that we collect from the separatory funnel. That should be a complete aqueous layer. For that halogenated waste, remember dichloromethane contains chlorine, so this would be part of the halogenated waste. And then you would just make sure to clean up the lab, clean the glassware, the hood, and the balance area, and then that would be it for the lab. All right. So I have a little practice problem for us to kind of work on together. So let's say we want to calculate the amount of the Z-stilbene that is produced after we have starting, or I guess with the starting materials of 10 grams of benzyl triphenyl phosphonium chloride and 3 mLs of benzaldehyde. And after we've run our reaction, we receive about 80% of the product. So something to note is that the ratio to E to Z stilbene is usually produced in about a 2-to-1 ratio. So the first thing that we want to do is actually find the limiting reagent between the benzyl triphenyl phosphonium chloride and the benzaldehyde. So to do this, all we need to do is divide the mass of the compound by its molecular weight. So starting with benzyl triphenyl phosphonium chloride, we have 10 grams of the compound, and then we divide it with 388.9 grams per mole, because that is its molecular weight. So the grams cancels, and what we're left with is 0.026 moles. What about benzaldehyde? So because we're starting off with a volume of benzaldehyde, we first have to convert it to mass. And so to do this, to convert a volume to mass, all you do is multiply it by its density. So we have 3 mLs of benzaldehyde times 1.04, which gives us about 3.12 grams of benzaldehyde. We can then do the same thing, where we divide 3.12 grams by the molecular weight of benzaldehyde, which is 106.12, and this leaves us with 0.029 moles. So now when we compare the two, we can see that our limiting reagent is our benzyl triphenyl phosphonium chloride. So from here on out, we're going to be using the, this number for the rest of the calculations. So now that we know the limiting reagent, we now need to find the total amount of stilbene that is produced. So remember that at the finale of the reaction, we received about 80% of a final yield. So that means of the limiting reagent, 80% of it was actually converted into benzaldehyde. So that means what we can do is multiply the amount of stilbene or the amount of our limiting reagent times 0.8 for 80%. And so 80% of our limiting reagent is about 0.0208 moles. So that means we should have produced 0.028208 moles of stilbene. We can then convert this to its mass by multiplying the amount of moles by its molecular weight. So the moles cancel, and what we're left with is 3.75 grams of stilbene. So finally, the last thing we want to do is find the total amount of the Z stilbene specifically. So remember that the ratio of E to Z is usually 2 to 1. So that means about 1/3 of our product should be in the Z stilbene configuration. So we just multiply 3.75 grams times 1/3, and what we're left is 1.25 grams of Z stilbene. So now we need to catalog our actual molecule that we synthesize. We need to make sure that we actually synthesize stilbene. So if we were to run an infrared spectrum or obtain an infrared spectrum of stilbene, this is what we would expect for trans stilbene to kind of look like. So the problem with the infrared spectrum is we only really have two functional groups, the aromatic and the double bond here that connects the two. So if we were to look at only these two functional groups, what we should expect is that around the 1500 mark to see the double bonded carbon stretch, which we can kind of see here. And then we see these large amounts of peaks here towards the left of 3000. So anything that is greater than 3000 is usually indicative of these carbon-hydrogen aromatic stretches. So the hydrogens that kind of come off here. So we kind of use this to get a good idea that, yeah, we have an aromatic and we have the double bonded carbons. So that is really what this infrared spectrum tells us. If we were to run the NMR, we get something like this, where we have a ton of peaks kind of just really close together. And that's because there isn't any really strong electronegative atom that can kind of act as an electron withdrawing group. So because all the hydrogens are relatively the same, they kind of get all scrunched up here. So here's kind of like a little zoom in of these three peaks here. So we can still kind of solve this by looking at how the peaks split. So here I've kind of shown the different types of hydrogens. So we have 4 different types. We have the hydrogens bound to our double bonded carbons, and then these 4 here that are next to them, and then the next 4, and then the last 2 at the farthest edges. So by checking the amount of splitting or the neighboring hydrogens to the one that we're looking at, we can kind of figure out which of these peaks belong to which one. So the easiest one to start off with is actually this blue one here. So for this blue, it has one neighboring hydrogen in the green, but no neighboring hydrogen here. So we should see a doublet, which is this one here. Moving further away from the center of the molecule, we get to the green ones, which should have a hydrogen over here and a hydrogen over here, which should give us a triplet. And then moving even further away, we should expect that the yellow should be our final peak. So it should have a hydrogen here, and it should also be a triplet. And so I believe this is a triplet. This is just like a very small signal that shouldn't really mean anything. So this should be a triplet. And so this leaves that this large major peak should be our red group, which is in the dead center of the molecule and has only one neighboring hydrogen. So I think you can kind of tell, but this is actually a doublet. So here's a thin line, and then it gets slightly thicker. So this would have been 2 peaks. So we can use the NMR to really figure out what, or kind of build our molecule from the peaks that we see.